Today's topic is section 7.3, use similar right triangles. Our goal today is use properties of the altitude of a right triangle. As you can see here, the altitude drawn to the hypotenuse creates two triangles similar to triangle ABC. So we have triangle ABC and we have this altitude drawn in here. Our altitude is segment CD. This creates three similar triangles. The first triangle we are going to draw is triangle ABC. Again, this is our starting triangle, triangle ABC. And now we are going to draw the two triangles that are similar to ABC. And to do this, first, we are going to draw triangles with the same orientation. And then we will determine what those two triangles are. All right. So, first one, I'm going to use this triangle in here. So, the first of the defining thing is the right angle, which on this triangle is D. One thing you'll note when doing these, if you have an original vertex, it does not move. So A and D are now defined, and our third point is C. And our third similar triangle, we have this triangle in here. Again, we have a right angle at D. We have original vertex B, which leaves us with C. We will now go back and add all of the lowercase measurements. So on triangle ABC, we had little lengths of A, B, C. And on the purple triangle ACD, we have that measurement CD is H, AD is X, and AC is B. And lastly, on our blue triangle, again, we have CD is H, DB is Y, and CB is A. We now have three similar triangles. So just like in chapter 6, we can use similar triangles and proportions to solve for any of little a, little b, little c, x, h, or y. The big concept out of this section is the geometric means of right triangles. If we recall from previously when we did geometric means, we had a over x equals x over b. And we would have two numbers and cross multiply and find the geometric mean of them. With this, we are working with triangles and segments of the triangles. And for a different explanation, you may want to look at page 451 for an alternative explanation to the method I'm going to show you. All right. In this method, our first one is the altitude. The altitude of the original triangle is segment CD. The altitude is the geometric mean of the two pieces of the hypotenuse it creates. So if you look at CD intersects the hypotenuse AB and creates these two segments, segment DB, or in this case labeled BD, and piece AD. And again, HYP I'm using to represent hypotenuse. So that is one of the geometric means you're going to see. The other one is the leg. And you'll hear me refer to this as the leg mean. CB, this segment here, is a leg of the original triangle. The leg is the geometric mean of the entire hypotenuse AB and the piece that is adjacent to the leg here, DB, that is also part of this geometric mean. So the leg is the geometric mean of the entire hypotenuse and the adjacent piece of the hypotenuse. And it does not matter which leg you use. So here we have in this case, the longer leg, but still the same holds true. The leg is the geometric mean of the entire hypotenuse and, again, the adjacent piece of the hypotenuse. And you'll notice this time the adjacent piece is AD, which is adjacent. It shares a vertex, point A, with the leg AC. How we use these is we determine what piece of information we have and what piece we are trying to solve for. So on each of these, we have a separate triangle. And again, it's the same diagram. In this case, the orientation is a little bit different, but we will label the given information. So, given a diagram at right, solve each situation. So if AD equals 4 and BD equals 9, solve for CD. I know that CD is the altitude. So I am going to use the altitude geometric mean proportion. So I know that the altitude, in this case CD, which I've labeled H, is the geometric mean of the two pieces of the hypotenuse, 4 and 9. It does not matter which order I put 4 and 9. So I could have 4 and 9 like I do, or I could switch those, because ultimately we are going to cross multiply and solve, and we find that H equals 6. Again, we are dealing with distances, so there is no negative value. So our final answer will be that 6 equals CD, the length we are trying to solve. The next one, and again, a completely different situation. If BD equals 6 and A to B is 8, and whenever you're doing a total length like this, a lot of times you'll see a line drawn outside to show that the whole thing is 8, and we are asked to find BC. Now, looking at the original triangle, the outside one, triangle ABCX, is a leg. So I know that BC is a leg, so I'm using the geometric leg proportion. So the leg, which I've called X in this case, is the geometric mean of the entire hypotenuse, which in this case is AB, which is a length of 8, and the adjacent piece, which in this case is 6. And just like before, I am going to cross multiply. I know that 48 is not a perfect square, so I'm going to break it down. Root 16, root 3, and I get that X is 4 root 3, which is the length of BC. In our last example, if AD equals 3, so we'll label AD as 3, and BD is 24, find the length of AC. And again, AC, when looking at the original triangle, is a leg. So I know I'm using the geometric leg proportion. So my leg, the unknown one, is the geometric mean, so that is y. And I know it's the geometric mean of the entire hypotenuse, but I was not given that. But in this case, I'm given both pieces. So I add those two pieces together. So 24 plus 3 is 27, which gives me the entire hypotenuse and the adjacent piece. The adjacent piece with y is 3. Again, I cross multiply, square root. I get y equals 9 equals the length AC. This one, a word problem. You are throwing a frisbee when it gets stuck in a tree. Luckily, your neighbor has a 25-foot ladder that they lean up against the tree, such that the base of the ladder is 5 feet from the tree. Your neighbor insists on tying a rope from the base of the tree perpendicular to the ladder for safety purposes. What is the length along the rope from the ladder to the tree? So we are going to there's our fancy tree, and we are going to draw a ladder. And we know the ladder is 25 feet long. And we know along the ground here that this distance is 5 feet. And of course, we're hoping that our tree is perpendicular to the ground. And lastly, we are going to draw the rope, which is tied from the base of the tree perpendicular to the ladder. And this right here is what I'm trying to solve, that purple length, x. Now, I know that x, in terms of the large triangle, is the altitude, which the altitude mean theorem says that x is the geometric mean of the two pieces of the hypotenuse, but we don't have pieces. And we can't put in and say one is x and 25 minus x or anything like that, because we'll have two variables, or in this case we would have to use y and 25 minus y because we've already used x. We'd have two variables, and that does not work. So what we need to do is look, is there another way we can do this? Well, yes, we know that this segment, the blue segment, is the leg, which is the geometric mean of the entire hypotenuse and the adjacent piece. Let's cross multiply. And we find that 1 equals x, which will be this piece right there. Now, once I found that what this piece is, there are two different ways I could do this. I could say that this is 1, and this piece here is now 24, and use the altitude, the geometric mean theorem. So I could say that x is the geometric mean of 24 and 1. Or I recognize that I have a right triangle, and I could say that 1 squared plus x squared equals 25 squared. Both are valid methods. Does not matter which method you use. So you solve both of these, and either way you solve it, you will get that x squared equals 24, and get that x equals 2 root 6. But like we said before, when you get 2 root 6, it's not necessarily an answer that you are going to want to give someone, so we will approximate it to be 4.9 feet.